In classical physics, we describe the center of a black hole as a singularity, a single point of zero volume and infinite density. However, modern physics suggests this is not a literal physical reality, but rather a warning sign. It is a limitation of general relativity when it attempts to describe extreme quantum conditions. We now interpret the singularity as a transition point where space-time geometry is replaced by something more complex, like quantum information networks. The information paradox is one of the deepest mysteries in physics. When an object, like a book containing unique information, crosses the event horizon of a black hole, what happens to its data? Classical theories suggested the information was destroyed. However, modern quantum mechanics tells a different story. The information is scrambled and encoded, but not deleted. In fact, today, approximately 78% of theoretical physicists believe that information must be preserved. This suggests our universe inherently protects the history of all matter, even inside a black hole. Outside a black hole, we perceive space and time as distinct dimensions. We move through space freely, while time marches forward in one direction. When crossing the event horizon, the laws of geometry shift profoundly. Inside, the radial direction and time coordinate effectively swap roles. The path toward the center is no longer just a direction in space, it becomes a time-like coordinate. Just as you cannot stop the flow of time here on Earth, an observer inside the black hole cannot stop their motion toward the center. The holographic principle suggests that the three-dimensional volume inside a black hole is actually a projection of data stored on its two-dimensional surface. Imagine every bit of information inside the black hole being encoded exclusively on the event horizon, like data etched onto the surface of a physical hologram. Just as a 2D hologram creates a 3D image, the physics inside the black hole may emerge from this encoded surface information, revealing the structure of space-time itself. This profound shift in perspective treats the interior not as a bottomless void, but as an emergent projection of quantum data. Deep inside a black hole, space is not empty. Modern physics suggests the interior is a dense, scrambled network of quantum information. These points are qubits, and their connections represent quantum entanglement. This web encodes the structure of space-time itself. If these quantum bonds were to break, the very geometry of space would dissolve. Here, distance is just a measure of how entangled these particles are. The firewall paradox once suggested that crossing a black hole's horizon meant certain incineration. Physics struggled with this idea, as it required a physical barrier where general relativity predicted empty space. Modern models have largely moved beyond this, replacing the fiery barrier with quantum entanglement networks. Instead of a break in spacetime, the horizon is now viewed as an entangled state. This allows information to pass through smoothly, preserving the continuity of physics as an observer crosses over. By viewing the interior and exterior as fundamentally connected through quantum entanglement, the paradox of the firewall effectively dissolves. In standard general relativity, the center of a black hole is a singularity, a point of infinite density where the laws of physics break down. String theory offers an alternative, the fuzzball proposal. It suggests there is no singularity. Instead, the black hole is a dense, stringy ball of quantum states. The entire volume is filled with oscillating quantum energy, meaning there is no interior void or point of infinite density. By replacing the mathematical artifact of a singularity with a structured quantum state, the fuzzball proposal helps bridge the gap between gravity and quantum mechanics. In modern physics, we are re-evaluating the foundation of reality. Instead of spacetime being the stage where events happen, we now suspect it is an emergent property. Think of spacetime not as a fundamental background, but as a meshwork emerging from deep quantum entanglement. Each node represents a qubit of information. The way these qubits are entangled creates the geometry of space we perceive. Inside a black hole, this system reaches extreme density. We can treat the black hole not as a physical pit, but as a giant, highly efficient quantum computer. Ultimately, gravity and space emerge from the patterns of information processed within this system. The interior is a manifestation of quantum state complexity. The event horizon is often mistaken for a solid surface, but it is actually a mathematical boundary. It acts as the threshold where space-time curves so aggressively that not even light can escape. Think of this horizon as a semi-permeable membrane. It captures and stores quantum information from anything that falls through, effectively trapping it from our perspective. When matter crosses this boundary, its quantum information isn't lost. Instead, it is imprinted and scrambled across the horizon surface, preserving the history of what entered. It serves as the definitive partition between the observable universe we understand and the radical, unknown physics within the interior. LIGO, the Laser Interferometer Gravitational Wave Observatory, detects ripples in the fabric of spacetime. These ripples, called gravitational waves, are emitted by cataclysmic events like binary black hole mergers. When two black holes merge, they create a unique signal. As the system settles into a single final black hole, it emits a ringdown, a characteristic gravitational wave echo. Recent observations of these ringdowns allow scientists to probe the structure near the event horizon. Deviations in the signal may reveal quantum hair, traces of information encoded at the horizon. The supermassive black hole at the heart of the M87 galaxy provides a unique laboratory. Continuous monitoring has provided crucial data on how spacetime behaves near an event horizon. For years, theorists debated if black holes could have naked singularities, points of infinite density without an event horizon shield. M87 SOAR data forces us to reconsider. Observation shows M87 Tatar possess a mathematically perfect, stable event horizon. This evidence effectively discards naked singularity models, reinforcing our understanding of general relativity. By shielding the singularity, M87 SMAR confirms that the interior remains hidden behind a stable boundary, guiding our search for a complete quantum theory of gravity. In general relativity, the center of a black hole is predicted to be a singularity, a point where all matter is crushed to zero volume. Mathematically, this leads to infinite density. In physics, infinity is a red flag. It tells us that our current equations have reached their limit and are no longer reliable. To resolve this, researchers are seeking a theory of quantum gravity. This would unify the smoothness of spacetime with the jittery, discrete nature of quantum mechanics. By replacing infinite density with quantum states, we move toward a model where gravity and atoms coexist without breaking the laws of logic. If you throw a book into a black hole, does the story vanish from the universe forever? Modern physics suggests that the information is not destroyed. Instead, the book is scrambled into the black hole's quantum state. The black hole acts as a perfect record keeper, encoding every page of that book into its complex, high-entropy quantum structure. The book doesn't disappear. It is fundamentally redefined as part of the black hole itself. Deep inside a black hole, information isn't lost. Instead, the interior acts like a massive quantum computer, using error correction to protect data. When matter falls into a black hole, its information is encoded into the entangled network of the black hole's own quantum state. This process is known as quantum error correction. Much like how digital data is made redundant to survive storage errors, the black hole spreads information across many entangled qubits. This distribution ensures that even if part of the network is disturbed, the original information remains stored and mathematically retrievable from the collective state. In physics, entropy is a measure of disorder. It represents the number of internal microstates a system can occupy. Simply put, the more ways a system can be arranged, the higher its entropy. Black holes are the ultimate thermodynamic objects. They possess massive entropy, meaning they store a staggering amount of information about the matter that created them. When matter falls in, its information is scrambled into the black hole's own quantum state. This is why black holes are defined by their incredible entropy. They essentially archive the history of the matter they consumed. Ultimately, the role of entropy in a black hole reveals that space and information are deeply linked. We are no longer just looking at gravity. We are looking at the deepest information storage system in the universe. For decades, we visualized the black hole interior as a bottomless funnel or a singular point of infinite density. However, modern physics suggests this classic model is deeply misleading. Instead, imagine a shimmering high-energy quantum fog. This region is not a void, but a massive chaotic state where space and time are fundamentally scrambled. We now view the interior as an encoded crystalline structure. Like a massive quantum computer, the information of everything that falls in is preserved, projected, and stored in a dense, interconnected network of states. Historically, we feared the black hole interior as a region of total destruction, a singularity where physics simply ceased to function. Today, the consensus has shifted. We now treat the black hole interior as a massive high-entropy quantum state, essentially a complex quantum computer. The core question is no longer what is inside, but how spacetime emerges from quantum entanglement. Most experts agree, information is preserved. Understanding the interior of a black hole is the ultimate challenge in theoretical physics. It represents the critical junction where general relativity, our theory of the large scale, conflicts with quantum mechanics, our theory of the subatomic. The black hole interior is the laboratory where gravity becomes so strong that it forces these two incompatible frameworks to meet. Solving this mystery is the key to the holy grail of modern science, a unified theory of everything. By cracking the code of the black hole interior, we don't just learn about gravity, we rewrite the rules of reality itself. The next decade marks a pivotal shift in black hole physics. We are moving from pure theory toward a synthesis of advanced mathematics and precise observational data. Observation and math will converge on a fundamental question. Do black holes possess a hard, singular center, or are they a soft, sprawling structure of quantum states? Over the next 10 years, data from space-based interferometry will test our limits. By 2036, we expect to see clear evidence revealing the quantum nature of spacetime. We have traveled from the classical notion of a singularity, once thought to be a point of infinite density. Today, we look past this myth, uncovering a profound mystery: the interior as a complex, emergent quantum architecture. The black hole interior remains our greatest frontier. It is a place where information is preserved, spacetime emerges from entanglement, and gravity finally meets quantum mechanics. The next decade of discovery will define our understanding of reality itself.